Right, so this video is going to be going over how we do the equations for epidemiological models. And we're going to start with a model that includes susceptible, which we will abbreviate as S. And these are people who can get sick, infected, which we will abbreviate to I. And these are people who are sick and are infectious, and recovered, which is people who are recovered and cannot get sick anymore from whatever infection we are modeling. And so when we're doing our models, we start with our process diagram. So we'll write a box for each species, one for S, one for I, and one for R. And we know that our susceptible people can become infected, and our infected people cannot recover. We don't have any other arrows because infected people aren't going back to being susceptible in this disease, and recovered people aren't able to be infected again, and then you can't go from susceptible straight to recovered without being infected first. So these are all of the arrows that we have. And then we want to think about what the rate is going to be for each of these arrows. So for our first arrow, which is the rate of infection of susceptible people, we're always going to say that we have some rate constant, which we're going to call Ki for K infection. And then we want to think about what this is going to be proportional to. So there has to be susceptible people in order for them to be infected, and those susceptible people have to be infected by some infected individual. So the rate at which susceptible people will get infected is proportional to the number of susceptible people and the number of infected people. So now let's think about our rate for this second arrow, which is going to be Kr. We always have our rate constant, and we try to call it something that at least somewhat makes sense to us. So Kr for K recovered. And the rate at which people are going to recover is going to be proportional to the number of people who are infected. So when there are lots of people who are infected, there will be lots of people who are then able to recover. If no one is infected, then no one will be recovering. And so those are our rates for the two arrows. And then we want to write our equations. So we write one equation for each box. So we'll just go in order. ds dt for the change in the number of susceptible people over time. And we want to just add up the arrows going in and out of the boxes. So this only has one arrow coming from it, and it is leaving. So people are leaving the susceptible group and going to infected at a rate Ki times Si. So our equation for ds dt is just negative Ki Si. And so we can also write an equation for the number of infected people and its rate of change over time, di dt. And I has two arrows, and so we want to include both of those. The arrow that is going in is going to have a positive sign. So people are becoming infected. We're getting more people infected. So that will be positive. And then people are leaving the infected group and becoming recovered at some rate Kr that is proportional to the number of infected people. And then we just have one last equation to write. Let me zoom it out so you can see the whole thing. It's going to be the rate of change of the number of recovered people over time. And that will be dr dt, and that will increase at that rate kri, because we only have one arrow going into the box for r. And so let's think about some other things that we could add to this model. Maybe interventions, maybe just, something a little different. So let us imagine that there is a vaccination. So I'm going to move these equations down. And so there's some vaccination, but you can only get it if you haven't had the disease yet. If you've already had it, it doesn't really matter because you're already immune to it. You're in that recovered population, you can't get sick again. So we're going to have some population of people who are getting vaccinated. There will be people leaving the susceptible, going into the vaccinated rate, and then they will also going into the vaccinated population, and then vaccinated people may also be still able to get infected, likely at a different rate than people who are susceptible and unvaccinated. So let's think about what the rates are going to be for these arrows here. So for this first arrow that's going from the susceptible to the vaccinated, we're going to have some rate kV, which is going to be the vaccination rate, and it will be proportional to the number of susceptible people. So the more susceptible people there are, the more people would be able to get vaccinated. If there's no one who's susceptible, then there's no one who's eligible for the vaccine. And in this second arrow, which is the rate at which vaccinated people are getting sick, we'll call this KVI for vaccinated infections. And there will be some value. Or let's think about what this is going to be proportional to. So there has to be a vaccinated person who gets sick. So for this arrow, for something on this arrow to occur. So it's going to be proportional to the number of vaccinated people. Those vaccinated people also are going to have to come in contact with an infected person in order to become infected. So this term is going to be very similar to the KISI term, where susceptible people are getting infected. It's just going to be proportional to the number of vaccinated people this time. And it is going to, this KVI term is likely going to be smaller. The rate at which vaccinated people get sick should be smaller if the vaccine is successful. Right, so now we need to put all of these terms in. And so we want to add these arrows to our existing equations. So let's look at ds dt. There's now a new arrow leaving the S box. So that will mean that we need to now also subtract the rate at which susceptible people are getting vaccinated. They're leaving susceptible, moving to vaccinated. And we've already said that that is going to be KV times S. Right. Now, when we look at our infected rate, there's a new arrow going into infected. And that's going from vaccinated to infected. So that will have a positive rate because it's going into infected. And we've already said that that rate is going to be KVI times V times I. Right. And there's no new arrows going to recovered. So we don't need to change anything about that. but we do need to write a new equation for our new species, dv, and that will be dv dt. And we know that people are entering this, there's an arrow going to it at the rate kvs, and an arrow leaving it at the rate kvi times v times I. And so this is now our equation for a case where there's vaccinated people. All right. I'm going to do one more example where this time I think we'll add quarantine to this model. No one had this as their intervention in class. Well, people had these separately, but no one had the two together. And so I'll just add the two together so you could see what that would look like. And so if we are going to quarantine infected people when they're sick at some rate, we'll now need yet another new box. We will have that be for our quarantine people, Q. And infected people are going into quarantine. And then our quarantine people are still able to recover from the infection. So let's think about what these rates will be. So the rate at which recovered people, or the rate at which infected people are going into quarantine, we'll say is some rate KQ, Q for quarantine, that is proportional to the number of infected people. More infected people, more people going into quarantine. And the recovery rate is still going to be KR, because we're going to assume that the people in quarantine are recovering at the same rate as the people who are still with the general population but are infected. And that is going to be proportional to the number of quarantine patients there are. So now we need to change to add some terms to our equations. So for our first equation, ds dt, no new arrows for s. For di dt, we do have a new arrow. It is leaving I going to q, so it will be negative. This is, and then that rate is kqi. And that's our only new arrow for I. We also have a new arrow for R this time, and that is going into R, and that is KRQ, so it's going to be positive KRQ. We don't have any arrows between V and Q, no new arrows for the V box, but we do need to write a new equation for our Q species. And so dq dt is going to be just the sum of its arrows. So the positive one is kqi, and the negative one is krq. And now we have written our equations for this full system.